Greetings. Today we will introduce the Wigner-Eckart theorem and also conclude the second unit. Now, we introduced in our last class certain vectors which were composed of the irreducible tensor operators and angular momentum vectors. Now, we were encouraged to do this by recognizing that angular momentum vectors and irreducible tensor operators both respond similarly to rotations, fact 1. Second fact, that angular momentum vectors are coupled using the Clebsch-Gordan coefficients. So, we asked if we could couple the irreducible tensor operators could be coupled using the same law of addition, and we discovered that indeed they can be coupled, and you get a new vector which is also an irreducible tensor operator, a new construct. By combining two irreducible tensor operators, we get a new tensor operator again. So, now we have a mixed creature which we know is a vector because it is the result of an operator x operating on a vector. So, the result of course will be a vector, and then you are summing over q1 and q2. So, it is a linear superposition of various vectors, and this will give you a new vector which I have denoted by this beautiful bracket on the left hand side. It could be any bracket, it does not matter. And our question is, what kind of a vector is it, and we expect it to be an angular momentum vector, and if it is so, it will need to satisfy the defining criterion for angular momentum vectors, right, and it should have similar response to rotations. So, we ask how does it respond to the rotation operator. So, the same vector written with all the labels with the full notation, because this is a vector which is made up of k1 and k2. K1 is the rank of this tensor and k2 is the angular momentum of this, right. So, k1 and k2 are like j1 and j2 indices. So, those are the quantum numbers, but one corresponds to the angular momentum vector, the other corresponds to the irreducible tensor operator. So, this is the full notation for the same expression at the top, and the Clebsch-Gordan coefficient is also now written fully over here, and we are asking how does this vector respond to rotations. So, what we will do is consider the response to rotations. So, the rotation operator is going to operate on whatever, it certainly does nothing to the scalar, which will just come out as a scaling factor, a multiplier, and then it would operate on this vector here, which is the result of the vector obtained by operating on this vector by the irreducible tensor operator x. So, this operator u is positioned over here, and in between over here I have inserted a unit operator. The rotation operator being a unitary operator, u dagger u is unity, and I have sandwiched a unit operator in between. So, there is no loss of generality there, and the advantage of doing this is that you can factor this multiplication, because operator multiplication is associative, it multiplies both to the left and right depending on how you look at this association, as long as you do not play with the order. The order you can play with only for commuting operators, but otherwise you can always have the association, and I can associate this unit operator which was inserted over here and look at what is inside this red loop, and this is nothing but the response of the irreducible tensor operator x to the rotation operator, and we know what that law is. So, we find that we have over here in this red loop the response of the irreducible tensor operator to rotations, and in this blue loop we have the response of the angular momentum vector to rotations, and both have similar responses, and we are able to get it by inserting this unit operator factored as u dagger u, of which this u we associate on the right and this u dagger we associate in this block. Okay. Now, we know what this response of the irreducible tensor operator to rotations is. Okay. You get a linear superposition of all the members of the family of irreducible tensor operators. The weight factors are nothing but the matrix elements of the Wigner D matrix, and likewise this also has got a similar response. And now you already have summation over 4 indices. There is a summation over q1, there is a summation over q2 over here. Now you have got a summation over q3 and a summation over q4. So there already are 4 summations. Okay. Now what do you have over here? You have a product of this D matrix element with this D matrix element, and you can look at this product using the Clebsch-Gordon series which we have studied earlier. Okay. And if you remember the result of the Clebsch-Gordon series, it expresses this product in a triple sum, and now there will be 3 more summation indices q5, q6 and q7. So there will be a total of 7 dummy indices over which summations are carried out. Although you can exploit orthonormality conditions and so on and contract them. Okay. And you know what the orthogonality relations are. So I will leave it as an exercise, and you can work out these contractions very easily by using the orthogonality relations. And it turns out that all of these 7 summations contract very nicely exploiting the properties of the Clebsch-Gordon coefficients and the orthogonality conditions, and you are left with only one sum, a single sum. All those 7 through the Kronecker deltas, they contract to a single sum, and the result is this, that the response of this vector to rotation is that you get a superposition of similar vectors with m prime going from minus j to plus j, and the weight factors, the coefficients, are nothing but the Wigner D matrix elements. What does it mean? That this beautiful bracket, this construct in the beautiful bracket, is also an angular momentum vector. Okay. It is not something that we were willing to take for granted, because we had not introduced it using angular momentum vectors. We had constructed it by coming up with a superposition of the irreducible tensor operator operating on an angular momentum vector weighted by certain Clebsch-Gordon coefficients, and then carrying out a sum according to a law which we know combines 2 angular momentum states. So we use the same law to compose this vector, and we find from the fact that it has the same response to rotations, it is actually an angular momentum vector, and you can write it in the full notation with all the indices plugged in. So k1 and k2, which were suppressed earlier, can be put inside as well, and this is our conclusion, that this combination, this method, this prescription of constructing a new vector actually gives us an angular momentum vector. You can also show, and this is also left as an exercise, that this vector is an eigenket of Jz belonging to an eigenvalue mh cross, and that the ladder operators operate on it just the way they do on angular momentum vectors. So these properties are not surprising, but it is good to work them out just to get confidence in this. Now we are ready to work with the Wigner-Eckart theorem. This was introduced by Wigner and Eckart independently around the same time, 1930 and 31, and what it does is it deals with the matrix element of an irreducible tensor operator. Okay. Now this is obviously important because physical interactions are represented by operators in quantum mechanics. It is physical interactions which cause the transition of a quantum system from a certain initial state to a certain final state, and this is denoted by a matrix element of this kind, that if omega is a certain operator, which corresponds to a physical interaction which induces a transition from an initial state to a final state, then this matrix element is a measure of the probability amplitude for transition from the state I to the state F, okay. And this physical interaction, which for us is now a certain irreducible tensor operator, we have now to look at the matrix elements of this tensor operator. Now the state I and the state F will be labeled by appropriate quantum numbers. It will be labeled by what we call as good quantum numbers. These quantum numbers would typically consist of the angular momentum quantum numbers, the quantum numbers of j square and jz. They will also include quantum numbers of some other operators such as a Hamiltonian. So there will also be an energy label, and essentially you will have a complete set of commuting operators or complete set of compatible observables which will give you the right set of good quantum numbers for the complete system, and the label I and the label F represent the complete set of good quantum numbers for the initial state and the final state respectively. And we are interested in finding what is the transition probability amplitude for the transition from I to F, and essentially we have to look at this matrix element. Now let us do a little bit of angular momentum algebra here, because we know from the defining relation that the irreducible tensor operators have got very specific well defined commutation relations with angular momentum operators. That is an equivalent definition that we have already learned earlier. So we take this expression which we are already familiar with, and we determine the matrix element of the operators on both the left and the right in angular momentum states. So we take this operator and take its matrix element in the state Jm and J prime m prime, and do the same on the right hand side, of which this factor comes out as a multiplier, and then you have to take the matrix element of this Tk q plus or minus 1 in the same states. Okay, so we begin with a relation which is an identity which comes from the definition of the irreducible tensor operator, and take its matrix element in angular momentum states. Now on the left hand side you have got a commutator of J plus with Tk and J minus with Tk. So you get two terms, Jt minus Tj, right. So you get two terms, and these are the two terms I have written on the left side, which is Jt over here minus Tj, but J subscripts are plus or minus, so I am dealing with two equations at a time, okay, one corresponding to the plus sign and the other corresponding to the minus sign. So you have two terms on the left hand side, here they are. Now this is something that we know, because we know how an angular momentum state responds to the ladder operators, and this is the same thing happening in the adjoint space. Okay, so we know the results of these, and we use those results and plug in that expression. So what is, how does Jm respond to J plus and J minus? You get the m index switched by unity, it goes either up or down depending on this ladder operator being J plus or J minus, and you know what the corresponding coefficient over here is. Okay. Now you can take the adjoint of this relation. So this is just the adjoint of this relation, and since this is an adjoint, the adjoint of J plus is J minus and the adjoint of J minus is J plus, they being adjoints of each other, you switch the subscripts over here minus and plus, and you have this relation here. Okay. So this J dagger plus minus becomes J minus or plus, but the right hand side is the same because the left hand sides are the same. Okay. So the right hand sides are essentially the same, but here we need the matrix element of J plus minus. So the plus is on the top and minus is at the bottom, so we have to interchange these two signs. So let us do that. So first, before I do that, I drop the label Jm, I change this label from Jm to J prime m prime. So, all the J and m are replaced by the corresponding primed labels, okay, because that is what I am going to have to insert over here. And now I have this relation for J minus and J plus, from which by interchanging these two signs I have the relation for J plus and minus, which is what I need over here. And these symbols, you know, this was minus or plus, so this is changed to plus or minus, and you have the same change in sign in every location. So, you have to do it consistently. It is very easy, but it is important to keep track of these details, otherwise it is very easy to make a careless mistake. So, now we have everything that we really need. We have both the relations, J plus operating on Jm and this one in the adjoint space. So, this is the relation for the adjoint space. We use both the results, and now you have the matrix element of this operator T in angular momentum states, because this result is plugged in from here, this result is plugged in from the first relation here, and now you have these multipliers h cross times the square root terms with the appropriate plus minus signs. You remember how we got them, and then what you are left with are one term coming from here, second coming from here. So, this is the matrix element of TKQ, which is this operator. So, there are two of these on the left hand side and one of this on the right hand side, whose index is different. Now, is this relation a little familiar? Does it look like something you have seen before? It looks like the recursion relations for the Clebsch-Gordon coefficients, right? It is not the same, but it is similar. It is obviously not the same. Okay? So, this is what we have got. These are the matrix element of the irreducible tensor operators, and the recursion relations for the Clebsch-Gordon coefficients have an exactly identical form, and you can study it term by term very carefully, and you discover that it is actually exactly the same, with the difference that the matrix elements of the irreducible tensor operators are replaced by the Clebsch-Gordon coefficients in the expression for the recursion relations. That is the only difference. Otherwise, they are absolutely isomorphic term by term. Okay? What it means that you have got a family of equations. These are linear equations, one in x and the other in y, okay, the coefficients being the same, right, because the coefficients are exactly the same. These square root terms, these are the coefficients, the square root terms, this one, then this one and this third one, and there are corresponding coefficients in the expression for the recursion relation for the Clebsch-Gordon coefficients. So, these square root terms are exactly the same, and when you have such a system of equations, then from your knowledge of linear equations you know that the ratios of the corresponding term must be exactly identical. Okay, that is something that you know from your knowledge of linear equations. Essentially what it means that xj is proportional to yj and xj over yj is a certain constant, which is a ratio. Okay. So, there is no very involved mathematics which we have to invoke in getting this relation, and what it tells us that if you take the ratio of the matrix element of the irreducible tensor operator to this corresponding term over here, which is nothing but a Clebsch-Gordon coefficient, okay, and all of you are now experts on Clebsch-Gordon coefficients. So, this ratio is what I have called as rho, and this remains the same no matter what the index is. So, this is our relation, and this ratio allows us to introduce what is called as a reduced matrix element. So, this is just a matter of notation, the same ratio. Okay. So, you have got a matrix element of the irreducible tensor operator in two angular momentum states, one is J m, the other is J prime m prime. Okay. You can use m double prime if you like, because here you have used m prime minus or plus 1, it is some index after all. Okay. So, you have got the matrix element of an irreducible tensor operator, it bears a ratio to the angular momentum coefficient, which is denoted by this rho, and you can introduce a new notation which is rather convenient, because this ratio is independent of the azimuthal quantum numbers m. Okay. It does not appear anywhere, but it does depend on the angular momentum quantum numbers and the rank of the tensor. So, it does depend on J prime, it depends on J, it depends on K. Okay. So, this rho has a certain dependence on J, J prime and K, and then you can write it as a function or introduce them as parameters or introduce some notation which explicitly tells us that this ratio is going to depend on J, J prime and K, alright. And this is a notation which is introduced, this is called as a double barred matrix element or a reduced matrix element. This is the definition of a reduced matrix element. Okay. This is the definition of a reduced matrix element, and you can take this coefficient in the denominator to the right by cross multiplying, and you have got an expression for the matrix element of the irreducible tensor operator, which is a product of this reduced matrix element or the double barred matrix element times the Clebsch-Gordon coefficient. Okay. This is just cross multiplication. And some books tell us that this is a theorem as well as a definition, because what it does is it defines the reduced matrix element. Okay. It gives us the definition of the reduced matrix element. We know that it came from the system of the linear equations that we solved by comparing the recursion relation for the Clebsch-Gordon coefficients with the relationship we get for the matrix element of the irreducible tensor operators, and this essentially is a statement of the Wigner-Eckart theorem. We have actually proved it, as you have just seen, and what is very nice about it is that it tells us that the matrix element of a physical interaction represented by an irreducible tensor operator can be actually factored into two pieces. One is this piece and the second piece is this. Okay. So, whenever you have a certain quantity which you can factor into two pieces, then you can look at each factor and get some independent physics out of it. So, this factor is the geometry, is that is where the geometry is involved. Okay. Because the axis of quantization is along, let us say, the z axis, j dot u is what can be simultaneously diagonalized with j square, right. So, j square and component of an angular momentum along some direction, whatever it is, some unit vector u, you can call it as z if you like, that is how you choose the z axis, but that is where the geometry is. And those quantum numbers which are coming from the eigenvalues of jz, or they are coming from the eigenvalue of j dot u. Okay. Those are the only quantum numbers which appear in the geometrical part, okay, because that has to do with the axis of quantization, which has got a certain orientation in space. The remaining part is what is called as a physical part. So, the matrix element of the irreducible tensor operator is now expressible as a product of two pieces, one is a physical part and the other is a geometrical part, and this offers great convenience, and you will see some of the applications as I will discuss now. So, this is the statement and the proof of the Wigner-Eckart theorem along with the definition of the reduced matrix element. So, the geometrical part consists essentially of the Clebsch-Gordon coefficient, and it is just a matter of notation because there may be some additional quantum numbers which I have indicated by mu, okay, because after all the quantum system is described by a complete set of good quantum numbers which come from eigenvalues of a complete set of compatible observations. So there may be some additional quantum numbers which you can indicate by mu and mu prime. This root 2 j prime plus 1 again is a factor which depends on the value of j prime, and the left hand side, this physical part, already has a dependence on j prime. So some authors include this root 2 j prime plus 1 in the definition of the reduced matrix element. It is just a matter of convention, so that is not such a big thing. So you will find some books in which this root 2 j prime plus 1 is not written, whereas in some books you will find that it is written, and it is just a matter of some convenience. You can always factor it out, and the essential ingredient of the Wigner-Eckart theorem is the factorization of the matrix element into a physical part and a geometrical part. So it has got very important applications, and the first one and one of the most important ones that I will discuss are the spectroscopic selection rules, which I am sure you are familiar with. Okay, everybody has some familiarity with what are known as the dipole selection rules, and you will see how they come into play. So now you know that because a transition from an initial state to a final state by any physical interaction is effected through this mediator, which is the operator sandwiched between the angular momentum states, and this matrix element is factored into a physical part and a geometrical part. If the geometrical part is 0, then of course the transition probability amplitude is 0, right, and when the Clebsch-Gordon coefficient goes to 0, if this q is not equal to the m1 plus m2, right. Okay, so these selection rules, the triangle law of inequality, because here in combining these Clebsch-Gordon coefficients, when you combine j and k to get a j prime, then j prime will belong to this range, to a minimum to a maximum, wherein the minimum is given by modulus of j minus k and the maximum is j plus k, right. This is the triangle law of inequality which is involved in the coupling of two angular momenta, and if this is not satisfied, the angular momentum coupling does not take place, it goes with the angular momentum coupling. Now this essentially gives you a selection rule, okay, because unless this condition is satisfied, the transition will not take place. What does it mean? This is the triangle law of inequality which we have discussed earlier. Now if this interaction is a vector interaction, okay, and let me use a result which you might have studied in time dependent perturbation theory. Now we will be independently dealing with this when we do some spectroscopy, and we will redevelop the Fermi's golden rule, but some of you possibly have an acquaintance with the Fermi's golden rule from your earlier course in quantum mechanics, and you will remember that the transition probability to a state f is given by the square of the matrix element, and then there are Dirac delta, there is the square of the coupling vector potential A, and so on, okay. So this relation we will redevelop again independently when we do spectroscopy, but for the time being I will use it to illustrate the application of the Wigner-Eckart theorem, because here you see that the transition is affected by this operator. You see the gradient over here, which is of course the momentum operator, right. This e to the I k dot r is coming from the vector potential, okay, and you can expand this e to the I k dot r in powers of r over lambda, lambda being the de Broglie wavelength of the electron, okay. and if lambda is large compared to r, compared to the atomic size. So you have what is called as a long wavelength approximation, which is equivalently a low energy approximation, and you can, when you expand in powers of r over lambda, the low energy approximation, the first low energy approximation is what you get when you set e to the I k dot r equal to 1, okay, take the leading term. Now this is what is called as the dipole approximation, and the reason it is called as the dipole approximation is because when you put this e to the I k dot r equal to 1, then you get essentially the matrix element of a momentum operator, and you will see that you can write this also as the matrix element of a dipole. Now the first step is to recognize that this matrix element is the matrix element of a momentum operator. You see that because of the gradient operator, so the I over h cross takes care of that, okay. And then you know that if you write the commutation between the position operator and the Hamiltonian, then this commutator is equal to I h cross over p times the momentum, which means that the matrix element of the momentum operator can be written as a matrix element of the RH minus HR, right. The matrix element of the momentum operator here can be written equivalently as the matrix element of XH minus HX. Now H0 operating on I either on the right or H0 operating on left on F, because it is a Hermitian operator, we know that anyway, right. So that will give you the corresponding eigenvalues, and then you have to take the matrix element of the position operator, and the matrix element of the position operator, the position times charge is the dipole, right. The position displacement times the charge is the dipole, which is why these are known as dipole transitions. So now we know what is involved in the dipole transitions. The dipole is a vector, so you have to take the matrix elements of an irreducible tensor operator of rank 1. A vector operator is a tensor of rank 1, so k is equal to 1, okay. The triangle law of inequality must be satisfied with k equal to 1, so j minus 1 must be less than or equal to j prime, and this must be less than or equal to j plus 1. All I have done is to recognize that I have got a dipole which is a vector operator, a tensor of rank 1, and this essentially tells us that delta j will have to be either 0 or plus or minus 1. So that is the selection rule, that a dipole transition can take place if and only if delta j is either 0 or plus or minus 1. Now so far so good, but you cannot have a transition from j equal to 0 to j prime equal to 0, and the reason this is excluded is very simple, because one must be less than or equal to j plus j prime, but if both of these are 0, then one cannot be less than 0 even in atomic physics, yeah. So delta j equal to 0 or plus or minus 1 is the selection rules, with the exclusion. So j equal to 1 to j equal to 1 is allowed because delta j is 0, but j equal to 0 to j equal to 0 is not allowed. So these are the dipole selection rules, and essentially you see that they come straight out of the Wigner-Eckart theorem in a very simple fashion. So there are some specific applications of the Wigner-Eckart theorem when you deal with the angular momentum operator itself. Now this relationship is valid for any irreducible tensor operator, and therefore it will be valid also for the angular momentum operator. So if you write the angular momentum, you can write it in Cartesian components or you can write it in corresponding spherical components. So you have got the spherical components of the angular momentum as j11, j10 and j1 minus 1, right, and this is nothing but the jz component, and because you know that this Clebsch-Gordon coefficient must necessarily have q equal to 0 for this particular component, it means that m and m prime must be equal. Okay. So that is you get that, and m must be equal to m prime. So that is what I put in the expression for the Wigner-Eckart theorem. I have k equal to 1, which is the tensor operator of rank 1. I have got q equal to 0, m prime equal to m, and now on the left hand side I can actually solve this relationship, because this is an eigenket of Jz, right. So this is an eigenket of Jz, and then you just have the projection of Jm on J prime m prime, which will give me delta J prime J and also delta mu prime mu, because of the orthonormality between the mu indices. So this is a very simple relationship. It has many applications in spectroscopy. You can strike out the common terms. You know that m prime must be equal to m. So this m on the left hand side must be equal to this m prime on the right hand side, and you get the double barred matrix element of the angular momentum given by the square root factor and bunch of Kronecker deltas. Now this angular momentum could be anything. It could be the orbital angular momentum L, in which case the square root of j into j plus 1 into 2j plus 1 becomes square root of L into L plus 1 into 2L plus 1, whereas if it is spin, and you know the value of spin, which is half. So if you just put half for these values of j, you get root 3 by 2 times h cross and the Kronecker delta between mu and mu prime. So the only thing I will like to mention here is a matter of notation, otherwise we are pretty much done with the angular momentum algebra and the Wigner-Eckart theorem. Is a matter of notation that in many books you will find that the Wigner 3j symbols are used. Wigner 3j is just defined in terms of the Clebsch-Gordon coefficient. Clebsch-Gordon coefficient you have handled quite extensively by now, and by carrying out this double sum you can express this in terms of the Clebsch-Gordon coefficient, but you can also have inverse relations, okay, because of the orthonormality conditions. So that is a simple exercise for you to work out, so I will not spend time on that. And there is a certain, this is again a matter of notation, essentially this is square root of 2j plus 1, but some books write it as, you know, j in a square bracket, in a rectangular bracket raised to half. So this is again a matter of notation, and here you find that these are the quantum numbers which go into the angular momentum coupling. Okay, the two angular momenta j1 m1 and j2 m2 couple to give you jm, but in the Wigner 3j the index here is minus m, so that the sum of these three m indices vanishes. So there is some advantage in having a notation of this kind. This is called as a Wigner 3j symbol, and depending on how complex the angular momentum algebra gets, sometimes you work with coupling of more than 2 angular momenta, coupling of 3 angular momenta, coupling of 4 angular momenta, because you may have multiple sources. When you have the angular momentum for a whole atomic system, then there are a number of electrons, each having its own orbital angular momentum, each having its own spin angular momentum, and you need to compose the addition of all of them to get the net angular momentum. We discussed this yesterday when we argued that it is important to define the angular momentum of a dynamical system correctly, because the corresponding angular momentum eigenstates must transform together jointly in the product space. Okay. So you often have to combine more than 2 angular momenta, and when you have to do that you introduce what are known as Wigner 6j symbols or 9j symbols. So the algebra becomes a little more complex, but not difficult. It is a little laborious, it takes time, but there is no new physics which is involved in it, and the basic elements of physics are essentially the coupling of 2 angular momenta. So with that I believe we are ready to conclude this second unit, and I will like to take up some applications in spectroscopy, which is the heart of atomic physics in a certain sense, and I will be taking a slightly unconventional route to this, because very often, even when I have taught this course earlier, I have introduced spectroscopy before I did the Dirac equation or the relativistic hydrogen atom. I have chosen to reverse the order. I will first do the Dirac equation and the relativistic quantum mechanics before I do spectroscopy, because an essential factor which is of interest in spectroscopy are, when you do things like Zeeman effect, you must know what an electron spin is, and you can plug in an electron spin as an ad hoc property. You begin with the Schrodinger equation and then say that you postulate that the electron has got an additional internal degree of freedom, which is the electron spin, and it has got a angular momentum and it has got a corresponding magnetic moment, but then it is like a postulate that you have to insert on an ad hoc basis. Instead, I would rather do the Dirac equation first, because when you do relativistic quantum mechanics, spin comes out naturally, so you do not have to make any ad hoc assumptions. Spin comes out naturally, and it is appropriate to do the relativistic quantum mechanics, because the Schrodinger equation is not covariant under Lorentz transformations. It cannot be, okay, because you have got the potential energy term in the Hamiltonian, which is space dependent, right, and space does not, it is not, a space interval is not invariant under Lorentz transformation. It is the interval in the Minkowski space in the space time continuum which is invariant, right. So the Schrodinger equation is not the correct equation of quantum mechanics, it is a very good approximation, and the reason you need to improve upon it is because the speed of light is not infinite. The speed of light happens to be finite, and that leads to various consequences. The major consequence is that of the special theory of relativity, and we will then find an appropriate quantum equation which is relativistically correct, and that is what we get from Dirac. So that will be our subject for unit 3. I will be using Bjorken and Drell's book, the relativistic quantum mechanics, for this purpose, and it is a very good book, and many of you might be able to get a handle on that. Now if there are any questions on unit 2, I will be happy to take, or else goodbye for now.